Hi everyone, my name's Hayden and my partner here is Ismail, and today we're going to tell you about our quantum Galton board project and also our self-motivated extension to stabilize quantum circuits. So the aim of this project was to produce a quantum Galton board that can give us different statistical distributions. So we used the paper that we were provided to implement fine-grained peg control, using a different value of theta at each peg to produce a different probability for the particle to move left or right. We successfully used this to approximate the binomial, exponential, and Hadamard-Walk distributions. You can see the latter of those at the bottom right on our slide. We also extended this ourselves to produce the Laplace distribution, which is at the top right. The way we decided to do this was to accomplish using an estimation routine to find the optimum thetas for each peg. So one of the key evolutions in our project along the way was to replace the total variation distance as our loss function with the Hellinger distance, which worked a lot better because it's effectively a smoother function, and that helps us to better estimate the gradients of the loss function. Next slide, please. So for our noise model, we used the generic backend V2 from IBM Qiskit, and we noticed that our implementation still worked well, but as we expected, it was significantly less good than the standard simulation, which is kind of what we expected. In the top left, you can see our Hadamard walk in the standard simulation, and the bottom left is under the noise model. So you should be able to see there the noise model is significantly worse. However, we still think it did a fairly good job at overall capturing the shape, and the TVD is still good at about 0.1055. We also optimized this implementation by selecting Cobula as the optimization algorithm. The reason we chose this one is because it's gradient free, and so it's quite rapid for low to moderate dimensionality, and it easily accounts for the bounds on angles that we needed to implement. So yeah, we also trained the trust region hyperparameter, and we found that increasing the different points we can start from as a hyperparameter was basically a really good way to increase the accuracy while keeping it low cost. We also did experiment with zero noise extrapolation as well. So in order to test whether or not we were successful, we implemented a range of different distance metrics to evaluate the performance, where we compared the expected and actual probabilities at each bin. For example, we implemented the Jensen-Shannon distance, the formula for which is in the top left corner. We implemented the Wasserstein-Wand distance as well in the top right corner, and also the Bhattacharya distance, which is in the top in the middle. We also implemented a number of others like the chi-squared statistic. You can see some of the example code on the left. In order to account for stochastic uncertainty, we performed multiple runs and averaged the results, which basically allowed us to eliminate the random noise on each run. We tested the metrics at the end for normality using a Shapiro-Wilk test. This is important because it's a condition for a t-test. We then decided to use a one-tailed t-test with a variable acceptability threshold to ensure that we could assess the accuracy of the quantum Galton board while accounting for stochastic noise. So this was implemented quite successfully. Some of our example results are on the right there. We also incorporated chi-squared functionality as well. And in the future, we would also control for systematic errors like drift. So now on to my colleague Ismail to explain our extension.
So for our extension, we decided to take a more unconventional route approximating to stabilizing our qubits with the noise. We decided to look at interferometry. So in the top left, you can see a Mach-Zehnder interferometer. Basically, interferometers are devices from optical physics, which use lasers or collimated beams of light, along with beam splitters, different types of detectors, to basically acquire information, both classical and quantum, about about photons and lasers and so on. They also formulate very neatly into this time evolution quantum circuit where we have a Hadamard followed by a time evolution operator, which we can use to apply relative phase to a qubit, and then we can follow that up with another Hadamard or information pulse, and then measure the qubit to determine to get these sinusoidal fringes, which basically allow us which work as a very good measurement of decoherence time in qubits. It's a standard method is to use the quantum circuit that's equivalent to Ramsey interferometry. If I just show you if I was allowed to show you the next slide. Okay, there we go. So basically, we can use this information, and from this information, we took a paper which has what's called a continuous drive stabilization operator. This paper basically devises a method of fixing a component of the block vector representing our qubit, and then using the relative, oh, that's too far, using effectively the drift in that component of the vector to stabilize the other two components with this equation. Now, this is a continuous analog operator because it's designed
Sorry,
for quantum sensing
Ismail, would you
applications.
mind getting to the conclusion? We are over time.
Sorry. Okay, so effectively we get to our stabilization routine. you can see in this graph here, we could show that it has an improvement over the normal model by applying small rotational gates to qubit, which we apply to the Galton board to obtain some better results. Thanks.
Some questions from judges.
I really like the interferometry step you did at the end. That was a neat extension. Very cool.
Perfect.
Can I ask a question as well? This is Ruben.
Yes, perfect. Yes, go ahead.
Did you test with different optimizers by any chance? You mentioned Cobila, another good one when you're using noise is SPSA, if you've heard of that one. In my experience, it does well when you're using a noisy system.
Yeah, so we did test with different optimizers. I actually can't remember the name of the first one we used, but it was a gradient-based method, and it was struggling quite a lot while we were using, especially the TVD, because it uses absolute values. It's not easy to find the gradient of the loss function. So we found that a gradient-free one, which samples, is actually quite a lot better, especially when it's paired with the kind of multi-start system we set up, because we found that was quite a low-cost way of getting better results. But yeah, that was one of the key evolutions of the project, was picking one that was relatively gradient free.
Great. Thank you very much.
Thank you.
And nice job.
Off to BiasQ.
I'm Nikhila, and my teammates, we are representing Team BiasQ. So the whole problem statement revolved around us making the Galton Box-style, like with quantum walks and Monte Carlo sampling. So our approach is primarily using Gaussian, exponential, and Hadamard walk distributions, comparing them against simulations, and evaluating the performance under realistic quantum noise models. So this is basically like how exactly we quantum algorithms can potentially speed up, and and giving us a faster solutions and everything. So this is a problem statement that we were trying to go. Like the classical Monte Carlo for diffusion, it scales with samples and steps, but in high dimensional or low latency, it becomes the bottleneck. So we are getting a different, promising alternative with Galton Box, like with the paper that we studied and the whole model that we ran. These are the results that we were able to implement. Like we implemented an n-layer quantum Galton board to produce Gaussian, exponential, and Hadamard distributions with, total variation, Jensen Shannon, and Wasserstein. So we were able to do with air noise models as well, like depolarizing, thermal relaxation, and all. Yeah. So these are the primary broader interference driven spread versus classical random walks. So this is one of the results that we were able to get, and this is the robustness under noise. So yeah, I'm just gonna give a minute for it. Yeah. So I'm just gonna minimize my it's disturbing me. Yeah. So noiseless versus noisy quantum Galton board under depolarizing and readout. So when it comes to the solution, we were able to follow this four points, like multi-distribution capability, scalable architecture. Like we were able to generalize to, for getting flexible simulation depth and noise aware design. We were able to do it with noise aware, tested with depolarizing, thermal relaxation, and comparative validation. So we also benchmarked against classical quantum, Monte Carlo methods. And we were able to achieve these points. Like we were able to generate Gaussian, exponential, and Hadamard quantum walks. We also validated the accuracy using total variation, Jensen Shannon, and we were also able to demonstrate noise tolerance and achieve really good results with statistical errors across all scales and scalable architecture. So this is one of the another results. Like this is like summary of statistical distance. If it's equal, it's like really perfect. It's lower, it's better. So how we got the results? So we built the circuit design, and we did the distribution control. Like we adjusted the coin bias angles to shape output probability. We were able to do the classical comparison, and we did the noise evaluation. We first tried to get it with IBM Osaka, and then later we were trying to in case there's no noise model, I mean, we were able to do it with the fake simulator as well. So this was able to measure real world performance and optimization. We also trying to kind of optimized it, like multi-run averaging and zero noise extrapolation. Excuse me. So this is unbiased quantum versus binomial. Like for the Galton board, we were able to achieve this. And when it comes to like exponential results, like this is like exponential target where logistic bias. So here we were able to like scale the resources like O of n squared quantum versus of 2 power n classical, and 60 to 70% gate reduction versus theoretical paper bounds. And we were able to get these results at the end. Like we were able to, like bootstrap uncertainty analysis, and then we used like like almost 8 distant metrics, but we fixed it to like 4 to 5 at the end, like Jensen Sharon and KL divergence, global variation. Okay, I'll just go to the final slide. So these are the results that we were able to achieve. We were able to go with the error mitigation and everything. And we were also able to apply to find Monte Carlo methods. And all this was able to give us a perfect realistic hardware noise model. So yeah, that's it. Thank you.
Questions from judges?
So this is interesting. That at the very last slide there, you showed a quadratic versus exponential advantage. Were you able to discern what kind of structures in the problem gave you that advantage?
Yeah, like when we were reading the paper, we were like we were like so curious about what exactly, like we tried all the metrics, like we tried everything that we could. So this is one of the things that we tried.
Hi everyone, Janvi, and today I'm going to demonstrate my project Quantum Box and Monte Carlo, and I represent my team JQC. So we can implement this Monte Carlo method, and we get the Gaussian curve here, Gaussian distribution here. So quantum walk is another kind of distribution which we get using the superimposition and interference, and which we can actually get using the quantum Galton board, where we can actually set the probabilities at each layer and we can get the distribution. Quantum Galton board, it actually provides exponential advantage over the classical counterpart. For us, the challenge was first to create the generic quantum Galton board and generate distribution for the quantum walk and the exponential distribution, and then to optimize the circuit and finally run the optimized circuit on a real QPU noise model. So we were able to create the generic circuit based upon the paper. And this is the Gaussian distribution that we got, the exponential distribution. We got this by increasing the probability at one end, and we use the RX gate for this. And for the quantum walk distribution, this is the distribution that we got. And for this, we had a different probability at the right hand side and the different at the left hand side, and we kept it at complementary so that we get the same peaks. And we analyzed the base circuit that we had, and we found it had certain weaknesses, like we were using 2n+2 qubits to implement this, and we were only using n+1 qubits to get the distribution data. So we were actually wasting 50% of data. Also, it was using large amount of this C-swap gates, corrective gates, as well as the inverted C-naught. So we wanted to reduce that also. So we worked on those areas and we were able to optimize. And this is the optimized circuit that we got for the quantum Galton board. And the algorithm that we use is this, that we actually use the Q0 as the control qubit, and the Q1 and Q2, they were the auxiliary, and they acted as a ball and cache, and the rest of n+1, it actually contained the probability distribution for the balls. Now, for n equal to 1, what we did was we initiate the Q1, which was the ball, and it was set to 1, and then we use the C swap gate, and then we use a swap gate. So with respect to the base, what we did was that instead of using a control C swap, we are just using a swap here, as well as we have removed the gate for the inverted C0. So by just this much amount of gates, we were able to realize for layer 1. When we go to the layer 2, here what we did was we stored the probability of Q3 to Q1 and the probability of Q4 to Q2, and then we repeated the same thing, that C swap and swap. So we followed this logic repeatedly, and this is the algorithm that we use, that for each ith loop we had the ball and the cache, and we did a C swap based upon the Q0, and then we did a swap and we got the previous distribution value in the cache, and then we did a swap again for the ball and the slot, and then we switched the functionality of the ball and cache. So we did a comparative analysis then with the optimized one, and we saw that we got a qubit improvement like we were using 2 times lower qubit, and we were using 2 times lesser amount of gates. Also, the execution time also improved with our optimized circuit. Like for n equal to 12, it took less than 10 minutes to execute on a 2V CPU, while for the base, it was actually taking around like more than 10 minutes for layer 6. And this is a quantum work distribution snapshot. We ran this for the on the noisy models using the IBM Brisbane. And for this, we actually removed all those data that had more than one, and we also scaled the data to 20K entries. And this is the snapshot of the distribution that we are getting on this noisy models. So we also did the KN analysis as well as the Basel-Stein distance analysis for the Gaussian exponential as well as the quantum walk distribution. And we found that the error rate was actually pretty low. So we were able to achieve a good accuracy here. Yeah, so we were able to reduce the gate count and reduce the qubit count as well as get like good accuracy on the distributions. But as a future scope, we'd also like to apply error mitigation techniques and run it on the QP for higher layers. And obviously, the limitations for us was the large wait time and the access to the QPUs. Thank you. Any questions?
I have a question. This is Ruben. I'm wondering, you might have mentioned it and I missed it. How many qubits did you reduce it to? So you said
2 times.
2 and plus 2?
Yeah, so initially we were using
half the number?
Come again, please.
Oh, yeah, please just continue.
No, I'm just saying we were initially using 2n plus 2 in the base, but we decreased it to n plus 4.
Great. Thank you.
So a little bit of another question that kind of following up on that one. Of the gate reductions and qubit reductions you got for this problem, how many of them would you say are specific to this problem versus a general strategy you could use for other Monte Carlo-like models?
I didn't get your question. Sorry, can you repeat, please?
Yeah, sorry. The question was how much of the gate reductions and improvements that you got in this algorithm were related, like were problem specific versus generally applicable to any Monte Carlo type problem?
It works for any. Like I tested it out with the Gaussian, with the exponential, as well as the this quantum works. It works fine. We are getting the same distribution that we got for the base one. So it is generic. It's not specific to anything. So here, if we are using this edge gate, this is for the Gaussian. But if you want to have it for any kind of finer control, what we have to do is we have to apply 2-qubit gate with ball acting as a control.
Got it. Thank you.
All right, is the next team ready? Konato?
Hello, my name is Evgeny Minaker, and I'm presenting the Quantum Walks and Monte Carlo project. I'm from Team Konato. So this work builds on a scientific paper that suggested using Galton board paradigm on quantum computer to model different distributions. We generalized this approach to more layers and to wider set of distributions. We built an optimized solution that can load virtually any distribution and studied the accuracy and scalability of the solution. So the Galton board can be viewed as a decision-directed acyclic graph. Beyond being intuitive and visual, it can be used as a mathematical tool to reason about and to design different distributions. I'd like to call it Galton board calculus. So the rules of Galton board calculus are very similar to a regular decision tree, but additionally, we can eliminate the nodes its probability to go left equal 1 because they're redundant and don't affect the final distribution, and that can be used for optimization. Quantum circuit resulting from the Galton board calculus is composed from the coin qubit, quantum pegs, and a classical register to measure the tally bin qubits, as well as n layers of swap gates controlled by the coin qubit. The resulting state is a superposition of Hamming weight 1 computational states. The non-optimized implementation of n-level board is 2n plus 2 qubits wide, and the depth is quadratic in the number of levels. And the simulations reproduce the expected Gaussian distribution when we use, let's say, Hadamard coin. And here we show the 12 levels on the noiseless simulator. Using the Galton board calculus, we could derive precise coin qubit rotations and to get a smooth exponential distribution, as we can see on the right. It also revealed redundancy in the Galton board packs with 1-0 probabilities, as we can see on the left, and that hinted about potential optimization. The Hadamard random walk bimodal distribution is slightly more nuanced. It requires stepping in superposition and maintaining interference across levels. Hence, we didn't reset the coin qubit between the levels, and we did add an extra swap layer to make the distribution symmetric. Otherwise, it will be left to right leaning. So, is our circuit optimal? Well, no, it's too deep and too wide for noisy devices. Smart transpilation is also not enough. So it was back to whiteboard, or should I say back to Galton board moment. And the solution was inspired by early observation that we made for exponential distribution. We applied the Galton board calculus again, and we kept only the side packs, effectively turning the decision DAG into decision tree. Given the vector of n+1 probabilities, we can calculate the exact angles of rotations for coin qubit such that each level is responsible for subsequent probability. And this way, we can load any distribution into the final state that we measure. This reduced the number of qubits from 2n+2 to n+3 and gave us a quadratic improvement for circuit depth, which is huge. Optimized circuits run faster and remain accurate under noise, at least up to 9 levels, and we measured it by Wasserstein distance and MSE mean square error metrics. Exponential distribution showed the best fidelity even at 14 levels. We confirm our results on real hardware. We ran it on IBM Torino backend with 8-level circuits, and it showed really promising and impressive results. We can clearly see the distinct features of each distribution. We studied the depths of the transpiled circuit against the number of levels, and it revealed that they grow quadratically in the non-optimized case versus linearly for the optimized case, which confirmed our quadratic improvement. A few words on the future scope of this project. So I see a potential in 3 main areas: education, research, and industry. For education, Galton board calculus is a great teaching tool. It's intuitive, it's visual, and the solution is easy to implement in different SDKs. We use Qiskit for this project, but it can be done in PennyLane, Classic, and others. In terms of research, we could study long-range entanglement with these Galton board states, and we can do it across multiple distributions if you, of course, optimize it further. On the industry side, I have a few ideas about QPU monitoring product, and I think that we could use circuits originated from Galton board calculus as benchmark and a monitoring tool for underlying qubits. So to sum it all up, we've demonstrated truly universal distribution simulator, and upon optimization, the qubits nearly halved, and circuit depths went from quadratic to linear, and preserved accuracy in the noisy simulation and even on real hardware. And we introduced Galton board calculus, another way to reason about distributions and engineer them in quantum computing. So thank you very much. Special thanks to all the sponsors that created these challenges, and good luck to all the finalists. Thank you.
That was excellent. So I have a question for you that maybe challenge you a bit. What do you do? So this is very good that you came up with like a almost like a mathematical formalism for this type of problem. So my question to you is, extending it, how would you deal with dynamic decision trees or dynamic graphs, right? Because in a real Monte Carlo problem, it's not always just a binary decision. It could be, you know, an n-way decision. So how would you change this to accommodate that?
Yeah, well, we could probably add more coin qubits. And actually, outside of this project, I did start experimenting with multiple qubits, etc. So we could have some joint distributions. And I did it both to maybe to optimize the circuit even further, because maybe the distance between the control qubits and the qubits that controls the swap and the qubits themselves play the role. So I think adding more coin qubits might be the way, but I do need to research it further.
Yeah, very cool. Thank you.
Thank you.
We'll move on to the next one, Quantum Pioneers.
Hi, everybody. We're the Quantum Pioneers. Jared Sampara. We also had Nero and Ipsita on our team. And today we're excited to present our work on quantum Galton board as a universal statistical simulation. This slide outlines the structure of our project. We'll start with a quick intro to our team, dive into what we built, including circuit design and simulations, then share our results and broader impact and ideas for future work. A bit about us. We're a group of friends who met at University of Massachusetts Lowell while doing research under the same quantum professor on various projects. This hackathon gave us the chance to collaborate on something we're all passionate about. For a high-level overview, we generalized the quantum Galton board to n layers for binomial distribution, extended it to general arbitrary distributions like exponential and ballistic ones, and tested it on noisy quantum systems using IBM's Brisbane backend, applying noise mitigation techniques to boost accuracy. Our starting point was reviewing the literature and implementing the 1 and 2 layer version of the quantum Galton board. We quickly spotted a repetitive pattern, layers stacked sequentially, and as we added more, the ball qubit representing the particles shifted to the board's center due to symmetry. This setup approximates a Gaussian for large n thanks to the binomial distribution it produces. Breaking down the circuit geometry, it starts with setup. Apply Hadamard to the control qubit for superposition and on X gate to the ball qubit. Positioned at index 1 plus n of layers. The core peg structure begins with a C knot at the peg center, flanked by staggering C swaps above and below to simulate branching. For each new layer, reset the control qubit, reapply Hadamard or a bias gate, and build the peg sharing C swap between adjacent ones to optimize. Repeat for n layers, then measure the position qubit, like collecting balls in a bin on a classical board. Here's sample code for the pegs and measurement logic if you'd like to try it yourself. We compute everything relative to the ball's position. To generate custom distributions, we modify the control qubit weight using an Rx theta gate. Instead of Hadamard from a quantum gate theory, the left deflection probability is sine squared theta over 2. So we derive theta equals 2 arc sine square root of probability, converting any desired bias P into an angle. For layers beyond the first, we add a correction term post-peg to maintain accurate probabilities. For a specific example, like the exponential distribution, we discretize the continuous exponential decay, which models processes like radioactive decay or diffusion, into L+1 bins. This gives the truncated geometric PMF, where R equals e to the negative lambda, which is less than 1, controls the decay parameter. Lambda controls the decay parameter. To implement, we calculate layer-specific biases for each peg in layer M. The left branch probability P sub M of K is derived from cumulative probabilities up to that point, ensuring the overall state encodes the distribution. And here's the code implementation for the exponential circuit. To test on real noise, we simulated using IBM's Brisbane noise model. We ran a baseline without optimization as control, then applied zero noise extrapolation, Z&E, by folding gates like H, CX, and C-swap to estimate ideal noise-free results, saving time while demonstrating improvement. To compare distributions via Kale divergence, Z&E reduced error noticeably by 2.89%, with gains growing as layers increase, provided its value for NISQ devices. This is for the 3-layer case. Looking ahead, we'd extend to integrated VQE for adaptive PDE solvers like Navier-Stokes and test more mitigation techniques for even better efficiency and real reliability. Thank you. And any questions?
That's very nice. Thank you. I like how you tie it to these different physical constructs, like the radioactive decay problem and diffusion problem and things like that. So there's one reason this model is so good for education is because you can tie it to many different things and you can kind of see like why the distributions are shaped the way they do in the quantum context. Thank you.
Yeah, I totally agree.
So to the next one's quantum probability pioneers.
Hello everyone, I'm Qazi Muqtadir Ahmed and I have my teammate Tasfia and Asif Mohammad Saad with me. We are quantum probability pioneers and I'm excited to share our projects on quantum walks and Monte Carlo. So the problem statement for this problem for our project was to implement a Galton board-like statistical simulator which simulates probability distribution for a given layer of Galton boards. So we implemented a quantum version of the classical Galton board or the Plinko game using quantum walks. Think of the ball as bouncing peg, but instead of classical probability, we are using quantum superposition to explore multiple phases paths simultaneously. Our key innovation, or the paper's key innovation in leveraging the quantum Fourier transform to achieve potential exponential speedup over classical Monte Carlo methods. We built this using Qiskit with parameterized circuit generation that works for any number of layers. We evolved from basic 1 to 2 layer models to a fully generalized n-layer algorithm. Our circuits can generate 3 different target distribution: Gaussian, exponential, and Hadamard. We tested across 12 IBM fake backends with qubits ranging from 127 to 156 qubits. Let me highlight our best results. For Gaussian distribution, we found the best results on IBM Torino backend. We measured 3 different distribution, sorry, can you give me a second? We measured three different distribution distance matrices: total variation distance, Jensen-Shannon divergence, and 1D Weierstrass distance. For Gaussian distribution, we got 0.0965 on TVD matrix. Jensen-Shannon divergence, we got 0.1023, and 1D Weierstrass distance, we got 0.2277. We also got similar values for exponential distribution and Hadamard distribution. So we also tested this similar. We also tested our circuits on IBM's new experimental AI transpiler, but unfortunately, we didn't have IBM subscription, so we couldn't access the AI transpiler fully, and also the AI transpiler is not really matured enough, so we couldn't use it. So that you can see the test results, they are not really accurate to the ideal. We used Qiskit transpiler with optimization level 3 to actually mitigate the noise. Okay, for the future scope of this work, we're thinking about extending this algorithm to higher dimensional quantum walks, integrating with quantum machine learning and application to specific PDE problems. We thought of one specific use case for this problem is to generate synthetic data with customized noise distribution. Let's say our problem has a very specific, the model we're trying to train has a very specific noise distribution in real world. So what we thought is, if we can generate a specific type of distribution or a distribution of a specific shape with the quantum Galton board application, quantum Galton board circuit, we can just use that circuit to generate that distribution shape and use that distribution to insert noise in a quantum data or any classical data set, which data set then we can use to train our other machine learning models to represent the real world data more accurately. So that was a presentation. Thank you.
Yeah, great job. We have plenty of time for questions.
So you mentioned mapping it to like an application specific problem. If you could just like think through in your mind like an application that you would map this to, how would you take the method you developed here and then map it for that application, right? So here, like whether it's like a Gaussian or whether it's an exponential, right? Those kind of had a known model for how you would set up the gates. So what if it's something where you don't necessarily know the distribution and you have to calculate it dynamically? Like how would you adapt it for that?
We were thinking we had to first map out the noise distribution of that problem first. Then once we get the noise distribution, if it's not a generic Gaussian distribution, or let's say if the noise distribution for that particular specific problem is not a Gaussian, not Hadamard, or not any known functions, it's just in a random shape, then we can actually simulate that random distribution shape with the Galton board framework. Then we can just move from there. And then we modeled our Galton board generator function in such a way that we can tune the distribution shape using the theta parameters of the RX gates. So then we just have to, for the mapping part, we just have to map the theta parameters to the shape of the existing problem.
So it's almost kind of like an unsupervised learning type of thing.
Yeah, yeah.
But you train it down to whatever the state of parameters that you need.
Yes, it's kind of like
Very
that.
cool. Very cool.
Great. And then we're off to a quantum ladder.
Good morning, everyone. My teammate Valentina and I will be presenting on the quantum Galton board simulation from theory to implementation and what you might expect to find on our GitHub repo.
We want to simulate a quantum board. Our purpose with the simulation is nothing but get unbiased and biased probability distribution, but also we want to optimize the design of a circuit by minimizing noise implemented from a real quantum hardware.
First, we explain what a random walk is. So the main takeaway is in one dimension, you can either move left or right for n steps. In 2D, move left, right, front or back. And the probability of finding you in a certain spot would follow both in 1D and 2D Gaussian type distribution. Now, a quantum walk, overly simplified, is the idea of going either both left and right, given a coin that it's both heads and tails. And after a number of 100 steps, we would get distribution like this. Again, this is overly simplified, more details in our GitHub. So now we want to extend the random walk to the classical Galton board model. So the main idea is a ball falls, hits a peg, and moves left or right with probability P or Q. If we add more layers to this board, we would get the same idea as the 1D walker, moving left or right given a probability. As the number of layers goes deeper, ideally approaches infinity, well, we get a normal distribution. Here are the results for 1, 2, 4, and 5 level Galton board.
Our solution basically is to extend this idea to a quantum model. Here we can see that the edge gates represent our ball and the Hadamard gate represents a 50-50 change of going to the right or to the left. If we want to bias this behavior, we just have to introduce a rotation gate that allow us to add a specific probability in the whole peg. We can do that also by adding a different probability to independent peg. Here we had the results for this. We had a normal distribution by using a Hadamard gate. We had an exponential distribution by adding the same probability to the whole peg. This is a more general case of that distribution, but also we can get a multiple time of distribution if we play with the rotation gate for every single peg.
Now, these were all noiseless simulations, so we run on fake Brisbane noisy simulation, and we plotted each possible outcome. So we can see we get a lot of dark green states that are not the ideal outcomes. This is for the standard quantum Galton board, and we also ran it for the biased and the fine-grained based. So the fine-grained based in particular is the one that presents the most results. The light green ones states are the ideal ones, the same as the noiseless simulation. So what we did, so our approach was really simple, is just remove the reset gates, which make up the circuit, because these are non-unitary operations and they're really destructive, and just add a new qubit. So we are swapping basically and adding more qubits. So what we got from modifying this circuit just for a 3 level is that we saw an improvement in certain states and a reduction in other states, even though we're using more qubits. Now, after that, we applied a matrix-free measurement mitigation routine, also known as M3. This is a post-measurement technique. So after applying the M3, what we got is actually our results that were already improved. They got a little bit better. And as you can see, the dark states, particularly the really ones, they got reduced by applying this routine.
Our impact is a reduction of the dip of the circuit of 32%, and our reduction of the gate uses is pretty much the same. Our future goal is to extend our methodology standard to the standard quantum Galton board and the bias one, and also establish a benchmark protocol to develop a specific error mitigation, combining different statistical routes to end with quantum peg model to Monte Carlo simulation focused on solving physical problems. That will be it. Thank you so much.
Amazing. Great presentation. All right, we have some time for questions.
Very nice. So earlier in it, you showed like with the Hadamard walk you have, it's kind of like you're preserving the superposition at each step rather than making a discrete decision. So in some of the literature, it shows that method actually can give you like an exponential advantage for some types of problems. But as you can see, the distribution is different. So is there a way to transform the quantum walk distribution that gives you the speed up and then unbias it in such a way that you could retrieve what the classical answer would have been had you made discrete decisions along the way? I know it's kind of a complicated question. I'm just curious if that's something you thought about.
The easiest answer would be I don't know. I'm not sure if that's possible.
I don't either. That's why I was curious.
No, but it would be worth exploring. That sounds really interesting.
Yeah. All right, very cool. Thank you.
All right, great job, guys. And we have last but not the least, Qubiteers.
Good morning, everyone. I'm Yashwant Balaji from India. And so my teammates Soham, Ankit, and we worked on this project in the past few days. So in this 5 minutes, we're going to present it in a brief way. We're going to tell our intuition and our total ideas. So talking about the quantum peg, so we can understand it in an intuitive way, like there are some n baskets and we have a ball going through all the baskets. So at each basket, the probability of it falling into the basket is P, and with the rest of the probability, it moves into the next basket. So that is a very easy way to understand, and we need to simulate it in such a way that it keeps on going for n layers, and we run it for multiple times and get the probability distribution. So for an n layer circuit and for the kth coin fall, we need to cascade it from k plus 1k till 0, 1 because it might have fallen in any of those previous cases. So that is the intuition, and we have one qubit to act as our coin, and the qubit is going to be reset after every run, after every layer. And yeah, applying this for n layers, we can get any distribution we want. Be entirely dependent on the angle that with which we rotate the qubit. So for an unbiased case of getting the Gaussian distribution, our angle is going to be half, and the probability is going to be half. So yeah, we need to choose a rotation angle in that manner. So after choosing that and generating the results, this was the result we got for this for a 12-layer QGB. And in an ideal case, our result was almost close to perfect. The TVD is 300 × -3. Yeah. Now coming to the exponential and Hadamard distributions, we have actually tried something different compared to the general QGB case. So we have a circuit, and this is the distribution that we're going to generate, psi equal to root pk into k. And so meaning to get a k value, we're going to be just using log n number of qubits, which is very less. Yeah. So in this way now, and this is also done by using rotation gates. So depending on the output we want, so we know the target distribution that we're gonna simulate, right? So depending on the distribution, we're gonna pick the angle values to get the distribution. So this is how we're picking the angles. And yeah, if we go into the results, if for exponential and for Hadamard works, we were able to go to very high n values and we got very high accuracy too. This is because our number of qubits required were very low. It was only log n. And yeah, the error was also close to 0. So by using this circuit, we were able to go very close to the results. So now coming to the case when we add noise. So when we add noise, the results are not close to ideal, but we were able to come up with an optimization technique to actually make them very close. In the Hadamard walk case, initially the results with noise were very bad, but by optimizing, this was the result. So let's talk about the optimization. So the noise can change the bias, meaning it will increase the probability of it falling to 0 or 1, even though we don't want it to increase it by that much. Or as the depth increases, the probability might add up and change a lot. Or even dephasing might be a noise that will change our Hadamard walk by a lot. So for all of these, there are quantum error correction techniques which can be applied. But we also thought of another method. So as you can see here, for QGB, exponential, and Hadamard walk, the alpha value and lambda value, these are supposed to be 1 in an ideal distribution, and we want the result where we want the thing as 1, but because it's deviating to something else, here we are actually putting them initially as something less than 1 or something slightly greater than or slightly less than 1. So when we actually run this with a slightly different angle as input, after the errors, the angle is going to change, right? Because that's what the error is doing, and by changing the angle, we might get closer to the real distribution. So that is the idea which we followed to do this optimization. And we took a grid of points. We took a huge grid of alpha values and all lambda values. And we ran this for all those values. And then we picked the thing which is closest to the ideal value. So if we do that in that way, the time taken for unoptimized is 0.1 and optimized is 0.3. and the results are very good. Like the gain was very good. So as you can see, the mainly in Hadamard case, we could do for 16 n value and very good accuracy. So yeah, our method advantage is basically our whole method relies upon the being able to generate for higher n values and a very unique optimization technique that we were able to actually optimize from 0.1 to 0.001 TVD values. So that is in a very brief way about what we did. Thank you so much. We only had 5 minutes, so we were pretty quick about this, but we would like to discuss more about how our optimization technique can be used to other approaches, because this is a very general technique. It is just changing the input, and we are assuming it might come to the correct output, and we have a grid of points to choose from. So this can be applied to any case, any depth of circuit without changing much values.
Great job. All right. Questions?
So I really like how you broke down how the different noise sources changed the answer that you get. That was very enlightening. Did you play around with the noise models at all to figure out like?
Oh yeah, like we actually tried adding only one kind of noise and then adding two different kinds of noise, and then we checked. So basically, some things make it more sharper and some things make it more diverge. But yeah, at the end, we thought so we can't have a single alpha value which will correct it. So if we have a grid of points which will reduce the sharpness, reduce the divergence, and do everything, then we can come to the ideal value in some case by going through them. So that was how we actually came to this technique.
So do you find that particular distributions are more sensitive to particular noise sources than others? Or is it all kind of the same spread around the different methods?
Some distributions basically depends on the distribution and the value too. Like some distributions we needed to have a very huge grid, like we need to go more places to find the value. But it also depends on the value of n. As n increases, we needed to, the grid size also increases. For this value of n, the 40k shots and the time was 0.3 and 0.1 for n equals 16. But as we go to higher n values, we needed to search over a lot of more grid values, meaning a lot of more alphas and lambdas and alphas for Hadamard. So that will actually be slightly time costly.
All right, very nice. Thank you.
Thank you so much.